All right, thank you. Can everyone hear me okay? Good. All right, thanks for the opportunity to speak to you today. I want to start right off by talking about the state-of-the-art 2012 in HPC. This is the Titan supercomputer at Oak Ridge National Laboratory, installed in and accepted in 2012. It was the #1 system on the top 500 list for 2012, some 16 or 18,000 nodes with Tesla accelerators, Nvidia GPUs at each node, some 27 petaflops of peak performance, around 17,000 or 17 petaflops of performance Rmax. The reason for pointing this out is it's a nice starting point to talk about the applications that Oak Ridge runs. It's an open science center, and many different scientific applications run there: material sciences, climate change. Obviously, it's a Department of Energy site, so lots of energy-related applications like biofuels and combustion. Thank you. Nuclear energy, of course. So in November of last year, there was a major announcement made about the follow-on system for Titan. And that system's called Coral. Coral stands for Collaboration, Oak Ridge, Argonne, and Livermore, which are the 3 DOE labs that conspired together for this particular procurement. And this is a significant step up. They specified they wanted a system that's 5 to 10 times faster. The system that IBM and Nvidia proposed and was accepted for 2 of the 3 systems that are going to be delivered. Procurement rules limited the winner to 2 of the 3 procured systems. Has only 1/5 the number of nodes of Titan, and yet it's going to be 5 to 10 times the performance on real applications. And there was a great deal of energy put into evaluating those applications and projecting performance. And I'll talk a little bit about that. It's part of the reason I'm speaking to you is to talk about the flexibility and how that node design came about. But it uses about the same amount of energy as Titan, around 9 or 10 megawatts to achieve that. I was in Japan a couple of weeks ago talking about this system because there's a lot of interest in this powerful of a design of an architecture. And for them, it seemed appropriate to compare it to the 2002 #1 top 500 system, the Earth simulator built by NEC, funded by the Japanese government. That system was actually #1 on the top 500 for 3 years, and its peak performance was a little over 40 teraflops. And what's kind of interesting is just one node of Summit has the same peak performance as the Earth simulator had in 2002, which is an interesting, mind-boggling statistic to start out with. What I actually want to do is tell you 3 stories today. The first of these is to talk about heterogeneous HPC. It's really the basis for the architecture philosophy at Nvidia around accelerated computing. And to do that, I want to talk about system evolution leading to that. Part of this tromps through some of my old history. I started out at CRAY Research back in 1980, working on the CRAY 1 with Seymour Cray. And from there, I think we can talk about architecture and technology underpinnings for the heterogeneous computing model that we advocate itself, and look at some of the rationale behind it. The second story is really one around architecture optimization. There's a lot of variability in the requirements placed on high-performance computing architectures by the applications that we want to run. And what we call the Tesla accelerated computing platform, really just a set of offerings and set of services and set of hardware and software components that we hope to allow our system partners and our customers to innovate on top of, are intended to provide that kind of flexibility to be able to optimize architectures for those applications. And a key component of that is something called NVLink, which is a node integration network, and I'll talk about that. And then finally, I want to come back to Coral and put a punctuation mark at the end of that story by just talking a little bit more about the applications and the node itself and the design, and encourage this to be viewed as an example of what can be done for other people's applications. It's a very awesome design, but the whole point of this is that optimized architectures don't have to be one size fits all. So in high-performance computing, we use really big numbers, and we talk about orders of magnitude, we talk about scaling, and we're on a very fast pace into the future, and sometimes it pays to look back as well. Often I find that we become inured to the scales with which we deal, and it's interesting when we look forward, an order of magnitude looks really, really large. When you look back, it seems like not such a big deal. If anyone has spent much time in a startup, perhaps as a CEO raising money with venture capitalists, you know that you can crawl at about 0.6 miles an hour with a suit on. If you're allowed to stand and run, you can do about 6 miles an hour. That's an order of magnitude difference. And that's a significant difference, and you'll notice that if you're trying to go someplace. But another order of magnitude puts you in a car going down the highway at 60 miles an hour, and another order of magnitude puts you in an executive jet at 600 miles an hour. So this is 3 orders of magnitude between crawling and flying in a jet at typical upper atmospheric speeds. And the interesting thing about this, I think, is that 3 orders of magnitude is kind of the millennial gap, the step that we like to advance things in high-performance computing. We set these goals at, I remember when we were trying to achieve a gigaflop with supercomputers, and then a teraflop, and then a petaflop, and now we're targeting an exaflop. And it's important to think about what each of those millennial steps means. It's a pretty aggressive thing. So I want to talk about HPC system evolution, which is kind of about memory architectures, because this has influenced the evolution of architecture and the evolution of computing resources and memory models, and that has had a major effect on application design as well. The canonical starting point is a single CPU and a single memory, and the example I like here in the supercomputing world is the CRAY 1. In 1976, first delivered, this is a 160 megaflops peak system. When I started working at CRAY in 1980, we were about as far into the future from a gigaflop as we are today, looking ahead, trying to get to an exaflop. So this is kind of interesting to me. What's really interesting about this architecture is that it had vectors and was really focused on latency hiding rather than latency reduction. There was no cache. Now, memory was pretty close because it was all static RAM and it was only a single CPU, but it really relied on streaming lots and lots of bandwidth and using vector registers that had 64 elements. You issue a single instruction, and these things would just pipeline stream through functional units, out through ports to memory, loads, et cetera. And you could overlap multiples of these. And it was very easy. People loved the CRAY 1 because it was very easy to sustain a high fraction of peak. And that's an important attribute in a supercomputer. Obviously, exotic cooling, had Freon running through aluminum columns, and the printed circuit boards were sandwiched on real copper plates, and the heat was conducted to the side with no fans. There were no capacitors in the system. It was all ECL, so it was perfectly balanced. It was really, really marvelous. The first LINPACK list in January of 1979 had a CRAY 1 at the top, around 100 megaflops. This is the top 500 supercomputing list. They started publishing them officially in '93 through 2012. 2012, the year of introduction for Titan. This is a CRAY 1. The pink line on the bottom is really number 500 on the top 500 list. The red line in the middle is number 500. And the top line is actually the aggregate of all 500. So you take all 500 systems, add up their Rmax performance on LINPACK, and that's the summation. That's why that curve is nice and smooth. And this was Titan in 2012. And interestingly, when we look forward to 2017 and the delivery of the Coral Summit machine, this is Summit, really. It's equivalent to all of the systems aggregate on the top 500 list in 2012. That's 9 orders of magnitude in my career, which is just pretty interesting to me personally. My wife asked me to try and put that kind of number into perspective, and I computed that it's essentially the number of seconds that we've been married, which is 36 years. And actually, it takes another 9 orders of magnitude to get to an exa, right? So I've been married for 1 exananosecond. Another interesting fact is that actually the 200 or so petaflops that we expect Summit to be, if you would have started up that CRAY 1 in 1976 and had it run at peak for the last 39 years, it would be up to 1 exa floating point operations completed right about now, or actually sometime in the next year. In other words, in 1 second, Summit's going to do that number of calculations and then do that number again the following second. From the single processor and single memory, obviously, we went to shared memories. The problem with shared memories, I mean, this is a really nice way to scale, especially if you have flat memory bandwidth, and it's not really worth doing if you don't. But the issue is that flat memory bandwidth doesn't scale. It's an n-square scaling artifact, and so you can only do it for a very short amount of time. I worked on the CRAY 2 as a designer. This had 4 vector CPUs and pretty much no change to the CPU architecture other than adding some semaphores, some in-memory means of setting and clearing flags so that the processors could cooperate on work. And this was really, at that time, a task-sharing. Microtasking or auto-tasking was just being developed, a way of kind of spreading outer loop across multiple processors in a lightweight way and still vectorizing the inner loop. This was a gigaflops capable system, had really huge memory. It was liquid immersed. It actually, kind of like the Pascal, used stacked memory. All the logic was stacked as well. Everything was 3D circuits. And it used DRAM. It was the first supercomputer CRAY made that had DRAM. And so the first system had 512 million 64-bit words of memory, which was more memory in 1985 than all of the CRAY supercomputers that had been shipped ever over the prior 12 years. The next step was a really big one, though. And this is where that crossbar broke. Right? We could not build it any larger. And also another convergence was taking place with microprocessors reaching a performance level where they were now as powerful or approaching as powerful or more powerful than the scalar processing capability of the vectors that we could build. And this was inevitable. Could have seen it coming, but it's hard for companies to get out of their own way. And it was a painful kind of transition. The innovator's dilemma confronted CRAY, and it took us a few years before we actually started our project. Along the way, actually, this last November was the 25th anniversary of a presentation, kind of famous if you're old like I am, by Eugene Brooks from Lawrence Livermore called Attack of the Killer Micros, in which he made many sardonic comments about how these microprocessors that had evolved in this highly competitive desktop and low-end server environment were going to eat supercomputing. And that same year, I got CRAY to actually formally launch the T3D project, the first massively parallel processor out of CRAY, the first non-CRAY designed CPU. We used the DEC Alpha EV4 microprocessor at 150 megaflops per processor, or megahertz, so 300 megaflop peak. The system had a theoretical peak of a teraflops, but that would have required like 2,000 processors, and nobody ever built one that big. But it was an interesting system. Had 8 processors per module. We could fit 512 in one liquid-cooled cabinet. The liquid cooling went through cold plates. And it was actually pretty performant given how early it was. These were the results from 2 NAS parallel benchmarks. One is the BT block tridiagonal benchmark. And you can see the vertical dimension in both of these charts is C90, single CPU C90 equivalents. The C90 was the highest end vector processor that CRAY was building at the time. It was the contemporary, the T3D. And you can see that 1024 processor T3D performed several times faster than a C90 on BT. But interestingly, on CG, conjugate gradient, not too surprising because this is kind of a memory bandwidth problem. The C90 actually kind of reversed that situation, showing that there were still some very significant limitations to what could be done with the MPPs. The follow-on generation, the T3E, had a number of advances. One of the advances was it was self-hosted. The T3D actually required a YMP or a C90 vector supercomputer to host it, which often was as expensive or more expensive than the MPP. The T3, though, actually pioneered a lot of the mechanisms that we find in modern NICs around latency, hiding agents, automatic management of message queues, block transfer engines, things like that, that we have to put around conventional CPUs because CPUs aren't designed to handle really long latencies and indeterminate latencies. Conventional CPUs are, tremendously powerful compute engines, but they assume that memory is right next to the chip. 1 clock to first level cache, a couple clocks to the next level, even just a handful of clocks to the cache that's on the board. And let's not even talk about, trying to go off node or anything like that. Only one or a small handful of outstanding references permitted, and really very small, sparse numbers of registers that could even act as destinations for loads, even if you could launch them. So we ended up building quite a shell around the microprocessor that represented essentially a NIC that was an agent that permitted it to communicate and interact with other nodes in the system without really, and still provided the microprocessor with an environment that looked a lot like what it expected to see in a workstation, for instance. So pretty much the same kind of technology. So in 2003, I kind of stepped away from high-performance computing and spent about a decade working in cloud computing and the like. And in 2003, there were still T3s in production. And when I came back to high-performance computing, I came back, this is my first job back in HPC. In 2013, all the T3s were gone, and I was pretty shocked to find that a single Kepler, 7.1 billion transistors, had basically the same memory bandwidth in aggregate of 1024 processor T3E, and the same same peak performance as an entire 1024 processor T3. So I was pretty blown away by this. I was talking with the director of CSCS, the Swiss data center. They have Thomas Schultes is the director. He has the number 6 on the top 500 list. Pitts Daint is the name of the supercomputer. It's a GPU accelerated computer, and he's quite an active computer scientist. And he said he was going through his attic and he found some old computer architecture books, and he was reading through an HPC book, and he was surprised to see this was like from the late 90s. And 20 years later, he said that there really isn't anything new in there. Yeah, I mean, there's some evolutionary things, some slight changes to topologies, but pretty much there's nothing really different. The big surprise, the thing that's really different that nobody anticipated was GPUs. And that was my observation as well. When I left HPC, clusters, Linux clusters, CPUs, MPI, things looked a lot the same coming back, except GPUs, and that was actually a big part of the shock. And it actually, I think, is important for us to think about because it's changing now the characteristic of what we think of as a node. This used to be a system, right? CRAY T3E with a couple teraflops of peak performance and hundreds of gigabytes per second of bandwidth. Actually, the largest traditional 32 processor multi-pipe vector system that CRAY ever built was the CRAY T90. It was the contemporary of the T3E. It had 56 gigaflops of peak performance and a terabyte per second of memory bandwidth, flat shared memory bandwidth between 32 multi-pipe processors. Well, that's Pascal. So, if you wait around for another year, you'll be able to buy this and stick it into your desktop system, and you'll essentially have a T3E's peak performance with a T90's bisection bandwidth. So, back in the 90s, when we made this transition to a distributed memory, everyone had to rewrite their applications, or you were only going to be able to run on one node. You had to distribute your data. You had to distribute your work, do a decomposition of your compute domain, and plot out your synchronization and how you're going to communicate, et cetera, because you weren't going to have nearly the bandwidth to communicate with between nodes that you were used to having in shared memory multiprocessors. And everyone did that, or most everyone. There's still some holdouts. And what's happened now in the 2000s is we've reached a point where because of Moore's law limitations, because of power limitations, et cetera, we've broken from having single CPU nodes. We now have multi-core nodes. In fact, thousands of cores are possible if you have a GPU accelerator at your node. And so we can think of our programming problem today. The MPI part is still the same. That part of your code you don't have to change. But we're now facing a refactoring of pretty much all HPC codes to expose all of that parallelism that you weren't thinking about that made up the code that runs on a node, to expose it and treat it as something that you need to synchronize, that you need to find a lot of fine-grained parallelism to distribute, et cetera. You have to start thinking about it almost as if you've got a T3E or T90 on your node. And this has led, I think, to some examination of that code. You look at it and you say, well, parts of it are serial. Lots of it is perhaps serial. It's I/O work. It's launching the application. It might be doing synchronization, et cetera. And then there's some set of loops or operations that are in functions or constructs that work on data structures. That's very parallel. And this is where the majority of the work is. And the whole notion behind an accelerated heterogeneous architecture is that we can distribute that work. If we can do this in a fine-grained enough way with low enough overhead so that we're not being defeated by AMDAHL'S law, then we can essentially use an extremely parallel processor that's optimized for throughput for the parallel sections and still have a screaming fast latency-optimized CPU for the system work and for any of those pesky serial sections that we can't get rid of. And so our whole job at NVIDIA, I think, boils down to that plus sign at the bottom and doing a really good job on somehow integrating those two parts of this optimized node. Now, we could focus, for instance, on the GPU side, on making it more and more general purpose and able to run system code and maybe do a little better job on serial performance. But all of that kind of optimization comes at the expense of parallel efficiency. Similarly, you can take CPUs and you can start adding parallelism to them, SIMD. You can start multiplying the number of cores, et cetera. But I would argue that you're never going to arrive at the same level of highly optimized efficiency that you would if that was your design goal and you started with a clean sheet of paper from the start and weren't concerned about compatibility, for instance. And I think you can make a strong argument for a heterogeneous computing model, even just based on simple AMDAHL'S law calculations. If you look at the many-core model, and this is like Knight's Corner, Knight's Landing, but it's not just Intel. If you look, their ARM processor vendors many of them are also proposing similar chips with tens of cores, up to 60 or more cores in some cases people are talking about. And those cores have been stripped back. When you look at the epitome of single-threaded performance, all of the features that people had put into, at Intel, for instance, had put into the design to do speculative execution and multi-way issue and really aggressive mechanisms for trying to somehow find a way through that serial path the code was going to follow in a minimum amount of time. Around 2003, Intel and other vendors all realized that a lot of that was way past the knee of the curve, that it was into diminishing returns, and that if you were going to go multi-core, you would probably back off from that and go with a simpler design. And when you go many core, or what I would call many weak core, because almost inevitably everybody weakens up the cores, back to that knee of the curve. So you go back to maybe a two-way issue, and you take out a lot of the speculation, and you start beefing up the performance of it by adding SIMD, et cetera, but you don't really improve its single-thread performance. When you examine the cost of trying to build a system out of just these many weak core chips, I think you run into some issues. And you can see this with a straightforward AMDAHL'S law analysis. So the bottom line here is, imagine we have a set of work, and it has a serial portion that has to be executed in serial. That's the orange. And it has a parallel portion that could be executed on multi-threads or vectors or whatever. And it has 10 minutes of runtime if you run it on a single core. Now I'm comparing two different scenarios. The top one is 2 sockets. It's a GPU assumed to be 10x the peak performance of the CPU that's in the CPU socket. And I'm assuming the CPU is basically the same CPU as the bottom reference. The second row there is 2 sockets of this many weak core variety. So I'm assuming that it has the same peak performance as the GPU, the same ability to parallelize as the GPU, but like the ARM chips, or like the KNC or KNL, the performance of the serial core on serial work is about 1/4 of what it would be if you were using a full-on Xeon. And you can see at 98% parallel work that the GPU and CPU is about the same performance as a pair of MWCs, and nicely accelerated. But things degrade pretty quickly. Even just going to 90% parallel work, you already have more than a factor of 2 difference. And it's not because of the parallelism, it's because of the serial. And of course, this just gets worse and worse, and it's not actually very long before the pair of MWCs is worse than just the serial runtime with a more powerful core. And I think this is the danger. This is an oversimplified analysis, and obviously, this is not a real code, but it represents, I think, the danger of that kind of approach and the value of having a kick-ass CPU as part of your node. So I think this bears out. When we look at performance then of our GPUs, of NVIDIA GPUs, we're never comparing just the performance of the GPU. We're comparing the performance of a CPU and a GPU. And when you look at the speedups that we achieve, for instance, with the K80, it's that kind of paired analysis. And when you look at the GPU, you see that there's lots and lots of parallel performance that you can put into a throughput optimized system when that's your sole objective. So, obviously, huge difference in the floating point that you can shove into those chips. And also, you can optimize for memory bandwidth instead of latency. And honestly, GPUs have terrible latency characteristics for their memory. But we don't care, because we have thousands of registers, and the entire chip is designed to hide latency and maximize bandwidth with no bubbles, minimize bubbles in every pipeline in the chip. And that's a completely different strategy, but it means that you can soak up arbitrary amounts of memory bandwidth. And that shows on applications as well. So we talk about this Tesla platform that enables optimization. And this is about providing some knobs for our system partners to turn. One of those now that we didn't have a year ago is different CPUs. So we have different CPU choices that people can make, even including x86 and Power and ARM, depending on the application catalog or the performance characteristics that they want from their CPU. And we think that's really important. Now, a couple of years ago, I'm aware, even though it was before my time, my tenure, people were talking about actually physically integrating some CPU cores on the GPUs, making them, quote unquote, self-hosted. I think this would be actually not likely to be a good idea. I mean, I use stronger words inside of NVIDIA when I say I think it's not likely to be a good idea. But there's lots of reasons for it. And it goes back to optimization for the role that you expect that compute pipeline to play. And, the CPU is optimized for latency. It has a much larger memory because memory that is optimized for latency is not nearly as expensive as high bandwidth memory. The GPU has much larger memory bandwidth, but correspondingly you end up with a somewhat smaller size memory. And again, the whole problem, the whole goal is, can we get these two to communicate in a way that appears to achieve integration without actually putting them on a chip? Well, if you put them on the same chip, what would be the downside? I think a CPU probably would not be very happy if it was hooked up to a GPU memory hierarchy. The latencies are probably on the order of magnitude longer. And the GPU memory controllers, even at the L2 cache level, are accustomed to delaying some references in order to align them with similar references coming from other threads. Remember, we know we're executing parallel work, and so we expect a lot of coherence between the memory streams, the addresses that are being streamed from all of the streaming multiprocessors to the memory controllers. And so we're willing to reorder things and juggle them, maybe delay one, and trade the latency there for bandwidth, and to keep our memory on the same page, for instance. We don't want to have to go through a full RAS-CAS cycle on DRAM and introduce bubbles. So, putting a CPU reference through that CPU is almost certain to stall. And the performance characteristic you think you're going to get out of, even a power CPU, if you put it on the same GPU and had it sharing that memory hierarchy, it's going to be significantly worse than what you would see on its own memory, what it expects to see. Similarly, the GPU is probably going to suffer as well. Remember, we're highly optimizing our pipelines and keeping them full with no bubbles. And we're exploiting coherency in the addresses that are being generated by all these threads that are concurrently executing within a couple of instructions of each other through parallel sections of code. And here you've got these CPUs that are executing who knows what, maybe a grep. And so any references that do slip into that nicely ordered pipeline are going to be bubbles, and it's going to slow down the GPU. In my view, what we want to achieve is a logical integration. And there's kind of two sides to look at that. One side is to look at it from the CPU's point of view. The CPU, we want to be able to reference and cache all of memory, the stuff that's attached to the GPU, the stuff that's attached to it, and be able to do that so that it doesn't have to transfer data back and forth and just eliminate that overhead. And the CPU, we want to be operating out of its cache most of the time. You want to be able to do atomic operations, et cetera. And so having cacheability is a key attribute of that link between the CPU half and the GPU half, the latency optimized and throughput optimized. From the GPU side, we don't really care about cacheability because we can hardly tell the difference between hitting in our caches and probably not hitting in the cache. As long as we get the bandwidth, we're happy. So mainly, we're interested in the bandwidth of that link. We want to be able to stream data at kernel startup, for instance, or when we're paging data with an out-of-core solver through the GPU's memory. We want to be able to access the system memory connected to the CPU, which is some multiple the size of the GPU memory. We want to be able to stream data in and out of that as fast as that memory can handle, as fast as the CPU can do it. And NVLink achieves that. We have these latency optimized and throughput optimized sides, and NVLink multiplies this bandwidth, and it has ultimately a memory semantic that allows the CPU to cache the data, no matter where it is in the memory hierarchy, and the GPU to stream at the same bandwidth that the CPU can achieve to its own memory. And that allows us to support things like unified memory, basically where we can have hardware hiding the fact that there's two disparate memories, and this makes it easier to port to and optimize for GPUs. So NVLink physically, it's a low power. It's about 1/3 of the energy to move a bit using NVLink as PCIe. It's about 5 times PCIe bandwidth per signal. And as I said, our goal here is essentially to be able to move data across it at the same speed that the memory can access its data, and also to ultimately provide a memory protocol that allows the CPU to cache. And ultimately, that is optimizing then this unit as if it was a single physically integrated system. You've probably already seen this slide. We're going to continue having PCIe going into the future, but these multiple CPU ISAs, a couple of them, are eventually going to have NVLink capability, native NVLink capability, starting with the Power 8+ in the Pascal time frame. But even if you don't have NVLink connecting your CPU to your GPU, if you have multiple GPUs, you can take advantage of the bandwidth that is provided by NVLink to connect together even just your GPUs. This is a study and evaluation. We don't have NVLink Pascals yet, but this is essentially a detailed evaluation simulation showing the value of having, in a PCIe-connected CPU situation, NVLink between 2 or more GPUs with several applications versus PCIe between those exact same GPUs. In other words, the situation we have today, which is PCIe, for instance, on K80 or in multiple other systems that people have built, or NVLink. And of course, it's proportional to how much the GPUs are communicating. But you can see that even for things like Fluent, you get a significant performance improvement just from having that improved bandwidth, assuming you're going to have the multiple GPUs anyway. And for something like 3D FFT that's bandwidth intensive, you get a real nice boost. It's like having twice as many GPUs. And this then kind of is our hallmark slide for the Tesla platform and the flexibility that it permits a system vendor to use to supply different optimized system ratios. There's a number of different topologies that can be supported with NVLink, and the next generation Volta multiplies that significantly. And that lets you optimize things. So back to Coral then. Coral is going to use essentially the world's most powerful serial processor, the Power 9 processor, which has NVLink. That's going to be connected with a coherent NVLink to our Volta generation GPU, which is, you can look at Pascal and Kepler and do that same kind of multiple in capability between Pascal and Volta, and the number is large. Coral essentially then is an exercise in what you can do with NVLink. And what we did is we took the mini apps, the DOE labs, Livermore and Argonne and Oak Ridge, put together a series of mini applications and benchmarks that represented their codes. And then there were a number of constraints on cost and memory size and other performance characteristics that were must-haves and like-to-haves. And we went through probably hundreds of different scenarios of different ratios of CPUs and GPUs and memory and interconnect and node size, et cetera. And what we ended up then was this system with approximately 3,400 nodes with IBM Power 9 CPUs, multiple Voltas per Power 9, integrated with NVLink, large coherent memory, over 512 gigabytes per node, all directly addressable, cacheable by the CPUs, by all GPUs and CPUs, and a really large integrated NVRAM on board the node, as well as a burst buffer. And did I mention over 40 teraflops of peak performance per node? And the performance extrapolations then for the Coral applications compared to the CPUs, CPU alone, and this is Power 9 CPUs, versus accelerated with the CPU plus the GPU, I think confirming the value of the heterogeneous architecture. So to summarize, I would argue that heterogeneous accelerated node architecture is extremely powerful and efficient, something you should cozy up to. You encourage your developer friends and your application owners to optimize for, because I think it's really the ideal situation. Every application has serial sections, and having latency optimized cores, retire that work as quickly as possible is very important. Throughput optimized cores for parallel work, and then high performance integration. We're using NVLink as that vehicle today. I think it provides a huge degree of flexibility, everything from one-to-one ratios up to Coral-like nodes. And actually, Coral is awesome. if it happens to fit your application profile, you should buy some. Open Power is not the same pricing structure as IBM Power because it uses open software stacks and has many members with different ownership relationships to the IP involved. And if you look at it, it's actually comparably configured servers even today with Open Power 8, comparing them to high-end Xeon. Maybe only a couple $100 difference between those, and you get a significantly more awesome Open Power-based CPU. But if that's not your cup of tea, it's just one possibility. We support multiple ISAs, and there's a lot of different variations on the theme that can be accomplished. So that's the end of my prepared talk. If you're not already a member of our registered developer programs, please consider joining. And if anyone has any questions specifically on my talk, I think I have a minute or two.